Hello, everybody. I'm going to walk you through my Kansas Fest presentation called Reverse Engineering Ted Nelson. I'm Eric Rangel, and let's go on a hyper adventure. Who is Ted Nelson? And why did we donate to scan his junk mail to the Internet Archive? Well, up here you can see his yearbook photo and what he looks like now, but that's just an artist depiction from his book, Passaplex. That's his autobiography. But look at these pictures that came from his junk mail that is now preserved. You got an old Heathkit ad, and those women are on PDP-4 terminals. And what else we got? Simplicity is the ultimate sophistication. An old Apple ad from the West Coast Computer Fair. PDP-7, nice picture of that. And there's a record in the back that I'll get to later. And then in the lower left, something from the Macintosh release. They had an 11-foot high model of the Macintosh. And he was into Apple computers. So he had a suggested retail price list from November 1979 when they were at Brandley Drive in Cupertino. So Ted Nelson is an amazing guy because he was at the forefront of the computer revolution when it was just starting. And he had great ideas in the 1960s. And he published a lot, so we still have those ideas, and we're reconsidering them as we enter the era of the decentralized web. Watch Silicon Valley if you want to know what that is. Okay, so here are his main accomplishments. He is the inventor of the back button. Thank you, Ted. His coworkers thought it would just be too complicated for people to understand that you're going to keep a stack of the pages they visited and you're going to walk backwards through the stack. But thank you for doing that. He claims to have created the first rock musical. Nobody else has stepped up and said they created an earlier one. And on his YouTube channel, he also wrote a soap opera, which is very funny, the computer theme. And his student film about the meaning of life is called The Epiphany of Slocum Furlow. So those are some fun things to look at. He coined the word hypertext in 1962 and many other words throughout his life. One of them is intertwingled, and we'll talk more later. His book Computer Lib actually encouraged Steve Wozniak to develop the Apple I. How about that? Thank you, Ted. And in his early career in the 60s, he designed a word processor called the HES, hypertext editing system, but he didn't like the way it came out. It was missing his great ideas about hypertext, but it was used by NASA because they had the money to buy it, and they used that for documentation of the Apollo missions. He designed full hypertext systems with visible connections to source material, and that's his Xanadu model. And that has been implemented in several different demos, and he had a full implementation of it in the 70s, the late 70s, around 79 to 80. And, but see, he was just a bit too early for the technology to catch up. The technology was just being born at the time. And what I find very interesting, he has a design for a multi-dimensional database structure that subsumes all others. It's like the extension of a spreadsheet, but say you could put cells between cells in any structure you like, in any dimension. So we'll talk a little about that later. Or you could email me. Okay, how do we reverse engineer Ted Nelson? People have tried. And his autobiography, Passaplex, is a great way of really seeing how his ideas came together over time. He's got a whole bunch of YouTube videos to help you learn about his opinions. And he wrote a letter to Brewster Kahle, where my hypertext ideas came from and where they all went. And that is a good historical narrative to put things in context. And all his junk mail, thanks to Jason Scott and Kevin Savitz, it's been scanned and put on the Internet Archive. So if you're looking for information about like audio equipment, microphones from the 60s or 70s, whatever he was interested in, he wrote and got catalogs for. So it's amazing that you could just now go back and see all that information. And I'll show you an example in a minute. Now, Sunless Sea was an attempt by researchers to collect information about the development of Xanadu. And that was the late 70s into the early 80s. So this was in the 2000s when an archive was created on the web to try to link together these early materials. And it can be found on archive.org now because they stopped paying for that domain name. So thanks archive.org for collecting the web since '95. Okay, so let's look at one of the gems in Ted's junk mail. Here's a record from Infotronic Systems, which is a vendor at the time that created an information rate changer. So let's listen to the record.
Mr. Dighton originally delivered this address in exactly 12 minutes, 25 seconds. It has been speeded by 50%, so that its running time on this record is only 8 minutes, 16 seconds, a saving of 33 1/3% in listening time. Now here's Mr. Dighton.
The conference of which this discussion is a part is directed toward innovation in the means of education. A half day is devoted to clinics for solving some 26 identified problems which managers face in effecting educational change.
Okay, so now we know that in 1966, there were only 26 problems with corporate education. I wonder, have we done better since then? Okay, so this is the homepage from Sunless Sea, the cyber archaeology project. Last revised in 2005. If Xanadu was the answer, what was the question? So they have links here, which thankfully link to documents that are on the Internet Archive. Some of them you have to do a little digging yourself to find, but it's great that we have this resource for historical research. And I think there is value to be found in these old designs. They just need to be brought forward into modern technologies. So, since this is Kansas Fest, what does this have to do with the Apple II? Nice cassette tapes there. Okay, that's the picture from the '77 WWDC, the Apple event. Okay, West Coast Computer Fair, actually. All right, so Ted adapted his 1972 design of JOT to create a product for the Apple II computer in 1982, and it actually required the BASICS disk, some 13 sector to 16 sector issue. And then Steve Whittam rebuilt that in Forth in 1986, and I'll be showing you that. It's on the Internet Archive, so anybody could go in there and play with it. Now, it's designed for a system that was to be used with a teletype and tapes, those big reel-to-reel tapes. So since you're just adding to tape, Ted designed a storage system where the text characters never moved. Only pointers to spans of characters were changed as the document was edited. And that's what made sense for a system where you're just appending. And what's interesting is the decentralized internet uses append-only logs. So it's time to revisit this concept. So here's the JOT page from the manual. So the Apple II Plus, you just turn it on. The Apple II, you turn it on and type PR number 6. That's assuming that you have an auto start ROM, I guess. And then you have, if you have a 16 sector system, you have to use the BASICS disk first. Okay, nice. So it was distributed on 13 sector, I guess, and weird. I don't know exactly. But yeah, Control E, it ends the document. So you had 2-drive system, and you would, there's some interesting cautions here, like computer grinds to a halt. Now you have 2 identical disks. Oh boy, Ted, nice documentation, thanks. It's a historical artifact that is great. Okay, so now I'm going to give you a demo of Jot. That's the actual disk label that Jason Scott scanned. Um, and this is the text that comes up when you run it on the Internet Archive. But I'm going to do this on a virtual machine in Virtual 2. Okay, so when you boot up Jot, this is what you see. I must invent my own systems or else be enslaved by other men's. Wow, an old quote that still applies. So to quickly show you what this does, if you press the space bar, okay, so if you press the space bar, it advances by one word. If you hit the return key, now you hear 2 beeps. So now you're advancing 1 sentence at a time. Okay, so now like here, there was a period there. If I press the space again, it finds the question mark and advances a sentence. And then if I hit return again, okay, that's 1, 3. So he was using the sound as a cue for the writer. So 3 means you're in paragraph mode. So the space bar advances a paragraph. So now watch how it's going to scroll the text. And it reads from the disk. So it's bringing in what it needs from the disk at the time it needs it. So now it's at the end of the paragraph. And so he designed it where the space bar is one level, and then the level above it is with the arrow keys. So like the left arrow key, when you're in paragraph mode, the left and right arrow keys move to the whole beginning and end of the document. So if I press the left arrow key, we're back at the beginning of the document. And then I could press the right arrow key anytime while it's displaying that, and now it's gonna move all the way to the end of the document. Okay, so he designed features that make it very easy to move sentences around and move paragraphs around. And that was really his goal, to have a reasonable system of cut and paste based on the way it used to be done with real paste. Okay, because that's where he worked. At the New York Times, he had to fill the paste pots. All right, so let's go back to the PowerPoint, keynote, okay, and continue. So a document is text plus pointers. And because this is done, you have all the old versions of the document. Every character is essentially a new version as you're typing. So you could reconstruct old versions. So as an example, if you had version 1.0, it was a dark and stormy night, which is position 0 of the document for a length of 30, and you want to change stormy to rainy, it would restructure the document to different spans of text. So you'd have it was a dark and, which is 1 span. Rainy is a new word appended to the tape, which would actually be position 31, length 5, and night would stay where it was, but you'd have a new pointer. So by adding these new pointers to the end of the tape, you're able to know that this is how you construct the document in the latest version. Very innovative at the time. Okay, so this Jot was written in Forth 1.7, and I believe that came on 13 sector disks at the time. So Forth is a really fun language. It's technically known as a threaded interpretive language. It's an interpreter like AppleSoft, but your words are constructed from other words. Programs are words. And it's very cryptic. People call it a write-only language, but it has very low-level access to the computer. You could write assembly language in Forth. So you'll see what I did with that. It runs very fast, small memory footprint, and it was primarily used for controlling machinery. And if you think about like animatronics, it can control sensors, and it's similar to an Arduino or a microcontroller today. And it's like Smalltalk in the way you could save the entire image and reload it. And I have done things with Forth, like say I create a music system where I put in a few songs and I save the whole system. I could load it back and all my songs are available in memory. Okay, so Forth has a ProDOS version called Mad Apple Forth. I haven't seen it anywhere else on the internet, so I put up my copies of those floppy disks. And the plasma language came as a derivative of fourth and another language. Okay, so this is JOT. So I wrote a disassembler to poke in the address that I want to disassemble and run, and I get the source code for JOT. And so it's like an incantation. But taking a quick look at it, rescue question mark. So a word that ends in a question mark usually is to detect an error condition and to exit immediately if that condition exists. So do you need to be rescued? Like if you messed up your disk, it'll handle that. Now look at the next three: 0, text safe, exclamation mark. So fourth uses a stack. 0 pushes the number 0 on the stack. Text safe is a variable that was previously defined, and the exclamation mark is a poke. So it is going to poke the number 0. So the exclamation mark reads the stack and it finds the 0, and it also finds the address of the text safe where it wants to store its variable value, and it pokes it. So here it's like saying text safe equals 0. And then, so it's very innovative. You just have to think in reverse Polish notation. Okay, empty buffers. So it sort of makes sense. You're going to empty all your buffers, you're going to load text, and that load text, that encapsulates all the reading from the disk and buffering to load your text into memory from your system disk or your data disk. Then text top, go to the top. Now he has cacophs. That means cacophony. Make a cacophony of sounds. And in case you haven't heard that, I'm going to start up fourth again. Okay, so if I'm in fourth right now. So if I type the word jot, which has to be in uppercase, it's going to reload the system and you'll hear the cacophony of sounds. That was it. Bwap, 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 bwap. Okay. Okay, so we'll talk about the sounds later. We'll again actually decompile the sounds, but let's take a look at Mad Apple fourth. It's a ProDOS image. You could run it from a hard drive. And here I'm defining words. So the colon defines a word. So the first line is saying colon, are you? And then dot quote, are you sleeping, quote. So what that's doing, it's adding a word to its dictionary called are you, and then it's defining that word in terms of other previously defined words. So dot quote is something that takes all the following text until you see the next quote and stores it into the memory where your word is being defined. So it's actually a print command. So when you run it, it is going to print that text, are you sleeping? So then I do the same thing with Brother John and morning bells are ringing and ding and dong. So then when I type ding dong, it prints ding dong. So now I could define another word ending using my ding and dong words. So ending is ding dong ding. And then when I run the word ending, it prints ding dong ding. So now I could define a word called frere Jacques. And here I'm using loop structures, but they're defined in fourth using a stack. So that 2, 0 do, it first pushes a 2 on the stack, then it pushes a 0 on the stack, and then the do looks at what's on the stack. It takes those two parameters and says, okay, from 0 to 2, non-inclusive. So I'll loop from 0 to 1. So it's going to execute the word are you, and then it's going to loop. So it's going to increment the 0 to a 1, and then it's going to run are you again, and then loop is going to increment to a 2, and it sees that it is it's supposed to stop, so it continues on. So it's going to run are you twice, brother twice, morning twice, and ending twice, and the semicolon ends the word definition. Then when you type frere, you get the whole song printed out. Okay, so I wanted to reverse engineer this jot floppy disk. So I started looking at it, and I noticed it has standard RWTS, but my problem was I wanted to list that fourth code, and it is obfuscated. He put some changes onto the disk so that you can't look at the list of words. So I had to play around with that. So he had a lot of null pointers. So what I had to do was write a program to find as many fourth words and addresses. And then I had to do some patches to fix the bad words, and then a program to fill in the null pointers. Now, I was able to do this because fourth defines a very strict dictionary structure where words point to their previous words. So I was able to look for those null pointers and know the address of a previous word and just replace it. So eventually I got a complete list of the fourth words and their starting addresses in memory. And then I wrote a program to disassemble the words, and using the Virtual 2 printer, I was able to print that disassembly to a PDF. Then I had some code to read, and I wanted to port it to Mad Apple Fourth, but it turns out it's a big system and it takes some analysis. But I was able to play with the sound routine as an example of how you would port that. Okay, so this is early on when I started to disassemble. I had some printouts, and that lower right shows all the fourth words and their starting addresses in the system. And Posiplex is Ted's autobiography. The Jot manual for the Apple II is above it, so you can see what it looks like. You gotta fold it in quarters. Well, now you do, but it was like a little handout. And some of the disassembly as I was looking at the RWTS and tracing that through. If you get frustrated through this process, get a bit banger. This is from Ted Nelson's junk mail. So apparently early on, people realized computers are frustrating, and they created a mallet for hitting your computer. Okay, so now let's try to reverse engineering Jot. So I have text files that I'm gonna paste in, and I was using breakpoints and the debugger to understand some of the code, and yeah, you had to keep notes. So my goal was to get an annotated source listing of the Jot system, which I have done, and it is on GitHub. Okay, first I want to show you the demo of Mad Apple Fourth. So I'm going to follow these instructions. So 3PR is a PR number 3 for 80 columns, PR number. Okay, so let's try this. Type, quote, readme. So some of these are extensions that I added to Mad Apple Fourth. So this types a text file. So this explains how I created my system. So there was a utilities disk which had some things that I wanted, like the case statement, a way to call the MLI for ProDOS calls, to save a system, and to type a text file. And I wrote an exec quote so I could execute a text file full of words, definitions. And so what was nice, I did all this, and then I was able to save it with my own version of Fourth. So this floppy disk that is available on my GitHub has these words. Now, one of them is object for assembler, which I'll talk about later. Okay, so now I'm gonna execute a Word file called mockbird or board.word. So this is going to add some Mockingboard functionality. So it's reading from the disk, and it's just a crude Mockingboard test. But basically in hex, I was able to poke in the values of the registers and do the Frere Jacques demo. So now I could type Frere. Now, I believe those slight timing anomalies are due to Virtual 2 running assembler code that's not 100% cycle accurate, but if anyone wants to play with that, go ahead. So yeah, so like the words are defined, are you and brother. Okay, so you get the idea. Now you could also do assembler programming. So I'm gonna type my aux move .assembler. So for auxiliary memory support, I coded in the aux move, and I did two routines, main to aux and aux to main. But if you look at the code here, this is how you code assembler in Forth. So here it's to the second parameter that I pass in, I'm loading, and I'm storing it at hex 3D in memory, and then eventually I'm JSRing to C311 to do an aux move, but it has an if-then-else structure to decide whether to clear the carry or set the carry. So I created an assembler, the object system that I created in assembler. It makes it easy to have parameters passed in and out of the system. The Forth system itself defines assembler words that have this if, then, else, and other control structures. Okay, and then you could get to basic from when you're done, and cat shows you what's on this disk. Okay, so this is available. Okay, so now let's actually reverse engineer this floppy disk and get to the source code of JOT. So I'm going to press Control E to exit the system. Okay, I have to click in here. Okay, so now we are in Forth, in the very limited Forth that JOT gives us, the obfuscated Forth. So I had to do some patches and then write some assembly code. I am not going to go into this. I just did this as a quick and dirty. Now, my problem is I forgot to go to the mini assembler. So I'm going to redo this when it finishes. Okay. You're watching a live demo, unprepared. Okay, so I'm in Forth. I want to go to the monitor. That's what I want to do. And then I could use the mini assembler by typing an exclamation mark and then entering the mini assembler command. So I could just paste this again. And now we are actually writing code into the address 8400, and it just ran it, and it patched the, at the end, there's another patch that it did. Okay, so we fixed Forth. Essentially. Now I wrote a word dump routine, and I had to do a few other patches. So we patch a few bytes, and then we write some more code, and we have that. And then we create a word name, something that prints the name of a word. Okay, so I wrote this a few months ago, and I forgot all about how it works. So, all right. Next, we have a word decompiler. All right, beautiful. Can other people code this fast? All right, and finally, a word disassembler. And then when this is done, 8700 is the address. So let's turn on the virtual 2 printer. Okay, so we leave this in the printer. What we do is PR number one control P in the monitor, and 8700G, and you have the Forth system being printed out on a daisy wheel, on a, it is daisy wheel, look at that, how nice. And that's the idea of how you reverse engineer JOT. Okay, so let's just go a little bit deeper. So this is how a Forth word is actually represented in memory. So if we look at 8118, you see an 83. So the upper few bits are used for certain control functions, but the 3 is the number, is the length of your word. So 4A, 4F, D4 is JOT. The A is the 10th character, the F is the 15th character, the O, and D4 has its high bit set, so the high bit marks the end of the word. So D4 is a T. Then you have the 6D80. So that's an address. You have to reverse it, 806D, and that points to the previous word. So this is the top of the Forth dictionary. JOT is the topmost word, and 806D is the next word, which is rescue question mark. And then EBE, the end of the first line, that is the address of the code that will interpret the rest of the word. So all words that are defined in terms of other words are use the EBE, which is it's a special type of word that can interpret other words. So 8077 is the first word to be executed when you run jot, and that translates to rescue ? So if you see that on the right, that 8300 is my utility for dumping one word after you poke 6 with the address. So looking at 8122, you have a B50F that translates to FB5, which is the address of the 0 word, which is a constant. Then 790F is the word text safe. So that's the basic idea of how you decompile a fourth word. Then you're going to find that some words have machine code. So looking at this one, 898 is the lowest word, which is lit, L-I-T. So you have an 83, 3 bytes. You have a 4C, which is an L, 49 is an I, and D4 is a T. Then you have 2 zeros. That's because there is no previous word. That's the end of your linked list of words. Then you have A008. Whoa, that's code. So you have the actual machine instructions starting at 8A0, which is, oh no, 8A0. 8A0 is the address. So the address points to immediately to the next instruction, 8A0. So the code starts with the LDA parentheses D9 comma Y. And that is the actual code for lit. So it is possible to fully understand how a fourth system works. Okay, so what I wanted to do was try to port some of this code. So I decided, let's grab the sounds. So from my listing, my disassembly, I found kakaf, and then all the words that it depends on. So looking at this list, looking at kakaf, it puts an 8 on the stack, then a 0, then a do. So to create that cacophony, it's just playing the sounds from 0 to 7. And I is the index, so it puts a 0, then it calls sound. So it's going to play sound 0, sound 1, through sound 7. Then let's see, I1 plus, it adds 1. Then, oh, muff. There's a muffler. Okay, so muff is a variable. If you look at 6C3E, muff F21 is a variable. So you fetch, so at is a peak. So you're fetching the value of muff and you're testing it to the sound plus 1. So like if you're on sound 0, you're gonna see is 1 less than the muffler. So this allows you to control which sounds get muffled. So like there are some modes where he only plays 5 sounds or 2 sounds. So he just changes the variable muff and that muffles the sounds he doesn't want to play. Okay, now 0 branch is a control structure. So really this was a do loop, but it got compiled into these low-level branching primitives. So it's like a go-to, but a test and a go-to. So if it equals 0, the next byte 8, it's going to skip forward 8 bytes. So then he has some pauses and some loops. So he loops back to FFE6. So that is a negative number to determine, it's like a go-to to redo the loop. Okay, so I just booted up Mad Apple 4th, and I'm actually gonna walk through actually doing this, rebuilding the source code. So I had to go through a process to read the source code and rebuild it. So at the lowest level, there is a machine routine called sweep, which does a sweeping sound, Okay, so let's play with that. So I had to rebuild it using my object machine language. So just to give you an idea of what it's doing, it's taking 8 parameters, and I'm taking the bottom of the stack, loading it, and storing it at the 8th parameter area. So it's really allocating 8 bytes, and I'm just reading from the 4th stack and storing the parameters into my own work area. And then incrementing X, that changes the stack pointer for fourth on its return. And then this is the actual code that I execute when my new word is called. So I'm defining the word sweep. So when I type sweep and I have 4 bytes on the stack, 4 addresses, that's 8 bytes, then it's going to execute this code. It's going to load the 8th parameter, store it at the parameter address plus 80, because there is self-modifying code in this routine. So I'm not going to explain it. It's on my GitHub, and I could talk with anybody who's interested. So let's paste it. Okay, so we're defining this assembler code right now. Okay, and then I have some tests. So we just created a word. Now, if I type words, we now have a sweep word. Okay, so let's test it. So I'm going to go to decimal, get out of hexadecimal, and I'm going to do some sweeps. Now, the way this sweep routine works is you have to give the address of the speaker as one of the parameters. So if you remember -16336, that's C030, that clicks the speaker. Okay, so that's a sweep up. Okay, and paste. Okay, so you could play around with these different parameters and learn how they work. So here is test-driven development. Code and test, code and test. And then put it in a notepad. Okay, so sweep down. And the last test. And this could be automated if anybody wants to play with that. Okay, so now just building up on what I saw in the source code, I'm going to define C030 as a clicker. So I'm going to go to hex. Okay, so now it's defining that value as a constant. So now he defines 2 words, click and glick. So I'm going to put those in, and let's see if you could hear it. A click, it's a little click. A glick, it's hard to hear. But you'll see how it's used later. It really gives you 2 different qualities of sound. So here, oh, here's a test of them. So let's define a test 1. Okay, so now we could type test 1. That's a short beep. And a test 2 uses glick instead of click. Okay, test 2. Okay, so it's a different beep. So now I have 2 test words. I can play them. Isn't this fun? Okay, then he defines an oscillator word, which uses glick. Okay, so let's paste that in. So we just defined an oscillator where you pass in 2 parameters and it oscillates. Okay, just play these so you could see them. So this is a good Hackfest project if anybody wants to mess around with it. You never used fourth before. And then he defines an oscillator over 2, which is a different quality of sound. Yep. So the programmer probably just found somebody who had written a sound routine and adapted it for fourth. Okay, so he has a pause routine, and then he has a clack and a cluck. So let's do clack and cluck. Okay, we define them. So you could type clack. It's a short click. A cluck is a few clicks. And now clack, cluck, clack, cluck. A short little series of clicks. Now here he defines the muffler variable. Get out of the gutter. Okay, up and down. Okay, so this changes the value of the clicker. No, it's saying clicker -1. These are just setting parameters for that sweep routine. So now here's the master sound routine that I re-engineered from his code. So instead of the 0 branches, I figured out that he was using a case structure. And so if it's a 0, he beeps. The 7 is a control G. The 1, cluck 1 plus, okay, clacks. So now you have the 8 sounds. So you could do 0 sound, and you get a beep. 1 sound, you get his click or cluck, whatever. Okay, so now here you can see how he's using the muffler variable. So if the muff equals 8, then it's going to play all the sounds. And that is what you heard when you, the cacophony. But actually, there are 2 more sounds. The cacophony only uses 5 sounds. Those other 2 are used in certain modes. So here is 6 muff. That is what you heard at the beginning. So it just played 0 through 5. And then if the person changes the sound mode, the muffler, to 3, it's really the control N key in Jot that the user can control which sounds are used. So here you only heard 2 sounds, 0, 1, and 2. And as a test case, I can store a large number in muff. And now everything is muffled. That's interesting. Okay, so now high and low, high and ho, I'm just testing a little bit. Okay, so let me click in here, define high and ho, and we'll do high, ho. Oh, I gotta change my muffler back. Let's do 8 muff. High, ho, and then high, ho, high, ho. Okay, now say I wanna save this. I've already saved it, but whatever I develop, I can save as my own file. So I believe I've saved Jot sound on this floppy. So if you want to just run it yourself, you just do dash Jot sound .exe. Exe, oh no. Okay, and now you have all the words to play with. Hi ho is in there too. So you could type hi ho, hi ho. Okay, and that's what I just did. Okay, so this ends my Kansas Fest demo. Let me just show you where I am on GitHub, where you could get all this document, all this fun stuff. GitHub.com/erangel, KFest 2020. Okay, so I have a README here. I have a bunch of links, all the links that came from my presentation. My presentation is here. For the 4th, I have my scripts. I have, yeah, this is all the scripts in the PDFs. So this PDF of the Jot disassembly has the entire annotated disassembly of Jot for those who want to study it. Okay, and what else do I have? The disk images are on here. KFest 2020. There we go. Also look at VCF East 2020 if you want to do more deep diving on Ted Nelson. Okay, so the disk images are here. So the Jot image, a copy of it, a copy that I modified for use at VCF, has some more explanations of how to use it. The Jot Sounds disk is the one I just showed you if you want to play around with the Jot Sounds. And the source disks for Mad Apple 4th, here's a bootable version. These all say unable to load ProDOS. Okay, and the mini assembler scripts here, if you want to go through what I did in the demo, the 5 scripts, the 6 scripts, complete word lists and Jot Sounds. Let me just see something. This is the, yeah, oh, okay. So feel free to email me, add issues to this. That's what I want to see, and pull requests. All right, thank you. Have a great day.